Hiya folks, Stuart here. We're back with another video for multivariable calculus, and today we want to talk about multiple constraints with a Lagrange multiplier method. Now, this is going to be our last video of Unit 3, so we've made it through partial derivatives once we finish this video, of course. Anyways, I will give an update on what we are covering in Unit 4 once we're done with this lesson. But anyways, let's not forget about how important Lagrange multipliers are. They're so important in the world of physics, and there's a whole field called Lagrangian mechanics where you will be using tons of differential equations, and you will also need to be modeling a lot of systems with constraints with Lagrange multipliers. So let's cover Lagrange multipliers with multiple constraints, because that does happen sometimes, and we want to be careful so that we know what we're doing the next time we try to solve one of these problems. Here we go. So the definition given f and constraint functions g and h. So just to be clear, f is going to be a function of x, y, and z, or however many you want, really. It can be generalized. G is going to be a function of x, y, and z, and h is going to be a function of x, y, and z. I don't know why I drew that h like that. It looks a little bit like eta, no? All right, anyways, if we do that, then we can write our equation such that the gradient of f at some point x naught, y naught, z naught is equal to lambda times the gradient of g at that point, plus mu, which is a new Lagrange multiplier, times the gradient of h at that point. So we've got nabla f equals lambda nabla g plus mu nabla h. So it's really as simple as that. So let's try an example. Find the maximum of f of x, y, and z equals x plus 2y plus 3z on the following curve. The curve is defined by the intersection of the plane x minus y plus z equals 1 and the cylinder, the unit cylinder, x squared plus y squared equals 1. Now what's this going to look like? So I'm not entirely sure what the plane looks like. I could have graphed this, but we don't need it really. Anyways, we've got the unit cylinder, and the unit cylinder makes something like that on the plane. So what we're going to have is we're going to have some skew, maybe, and then we're going to have a curve that goes in a circle, but it's going to be an ellipse. It's going to be kind of an ellipse now, looking at it from its normal, and it's going to look kind of like that. So that's going to be our curve, and we want to find the maximum of the function on that curve. Now, because we're dealing with three dimensions, it's kind of hard to imagine this. But anyways, because we're equal to 1 here, we can set our constraints. So nabla f equals lambda nabla g plus mu nabla h. So we have g equals 1 and h equals 1. So now what we're going to do is we are going to find all of our gradients. This is a very easy gradient to find for f. Differentiate x goes to 1, differentiate 2y goes to 2, differentiate 3z goes to 3. Differentiate for g, x goes to 1, y goes to negative y goes to negative 1, z goes to 1. Finally, x squared goes to 2x, y squared goes to 2y, and z, we don't have any z's, so we get 0. So we got 1, 2, 3 equals a lambda times 1, negative 1, 1, plus mu times 2x, 2y, and 0. So that is our equation. So that forms 3 equations for us. So from here, we can actually solve from this bottom equation. The bottom equation gives us 3 equals lambda times 1 plus mu times 0. So that cancels out. That cancels kind of. So we get lambda equals 3. So if we get lambda equals 3, we can plug into the other equations. We get 2x times mu equals negative 2. Thus we get x equals negative 1 over mu. Then we get y equals 5 over 2 mu. Now we are able to solve for mu by plugging into the cylinder equation up here. So we get 1 over mu squared plus 25 over 4 mu squared equals 1. Now we can solve for mu. We get mu equals plus or minus the square root of 29 over 2. Now we can plug this in for x, y, and z using our little equations. So thus we get x equals minus plus 2 over root 29, y equals plus or minus 5 over rad 29, and z equals 1 plus 7 over rad 29. So now we will solve for f of 2. We're going to take the positive case. Get negative 2 over rad 29, comma 5 over rad 29, comma 1 plus 7 over rad 29, and we get 3 plus or minus the rad of 29. So we can determine the maximum. The maximum is obviously going to be the positive case. So thus we find the maximum of f on our given curve is 3 plus the square root of 29. Thank you for watching today's video of 3 deviations. In the next video, we are going to start talking about multiple integrals. So double and triple integrals, that's going to be our next unit. It's a pretty challenging unit, but it's not as bad as vector calc, which will be our last unit. So we'll get into that, and we're going to really slow down to discuss multiple integrals, kind of like we did for partial derivatives, so we get a full understanding of what they are, what they mean, and how to use them. So thanks for watching, and we'll see you in the next one. Bye.